This video will be covering finite limits where your variable would approach a real number. So here, a would be an element of the reals rather than something like infinity. So a limit can be used to describe something like a hole in a function or when something approaches a number you cannot reach. For example, here maybe we have a curve and there is a hole here. Clearly, it is represented in the graph, but it never actually makes it to this point. So we can say that the limit as x approaches 3, since our x is getting closer and closer to 3 from both sides, if you look at it this way and this way, is around, I don't know, let's say this is at a y equals 5. Let's say we can, as the limit of x approaches 3, this function can be evaluated at 5. So this doesn't mean that if you plugged in 3 into your function, you would get 5. This isn't true because you can see there's a hole here. It just describes the behavior of the graph as it gets really, really close to that number. So you might have also come across left and right hand limits. So a left hand limit would be something like x approaches -4 from the left hand side. So there'd be a little minus sign here to indicate this, meaning it comes in towards the x-axis from the negative side. So maybe we have a graph like this. So notice how from the right hand side and the left hand side, the y values are different. You would maybe see this in a piecewise function. So as x approaches -4 from the left hand side, remember, negative inwards towards the x-axis, this can be evaluated at, I don't know, let's say this is 2 and this one is at 5. So we would have to evaluate this one as 2. And from the positive direction, sorry, -4, positive direction, this would be evaluated at 5. So the reason why we need left and right hand functions to, left and right hand limits to describe functions is because this can be a scenario where this limit does not exist at all for this function. And that is because these two limits do not agree. When your left and right hand limits do not agree, you do not have continuity, meaning that your limit does not exist, since it wouldn't make sense for it to. There are 2 points here. So, using this, we can use limits to solve equations. So here we have something that you normally wouldn't be able to do. If we had f of x, or sorry, f of 1 was equal to x squared plus minus 2x plus 1 divided by x minus 1. In the bottom here, we would have 1 minus 1, meaning a division by 0. So this is not possible if we just plug the number in. So instead we can use limits to evaluate what y value this hole would be at. So the way we're going to do this is by factoring the upper term here. So as x approaches 1, x squared minus 2x plus 1, something that multiplies to 1 and adds up to -2x. So that would be x minus 1 and x minus 1, all divided by x minus 1. You would see that 2 of these would cancel since it's just a fraction. And the most important rule in limits is that when something is within the domain of the function, so now we're left with x minus 1, we can just straight up plug the number in. This makes this stuff a lot easier. So now we'll have 1 minus 1, which is equal to 0. This means that at where your hole is supposed to be, I don't know what this graph looks like, but let's say it goes down like here. There's a hole here at x equals, sorry, there's a hole here at x equals 1. The y value of this hole would be 0. So you can see how limits can allow you to perform operations that you previously couldn't through factoring. You can think of it as removing the hole from the equation so that you can look at it graphically.